Hello and welcome back to another video. Today we are learning about proof basics and reasoning. This is the first lesson in our third unit called Introduction to Proofs. So everything in this unit is going to be about proofs. Before we can get into solving a proof, first we need to know what a proof is. So here we have a proof is an argument that seeks to establish a fact or something true using logic. I'm going to go ahead and highlight that because that is pretty important. It is also a series of statements that leads to a conclusion. However, each statement must be supported by evidence. We have evidence that is given in the form of postulates, definitions, theorems, etc. We'll use a lot of theorems in this unit. We previously have had a few postulates and a few theorems, and we're going to learn even more. A proof is why we are allowed to say what we're saying. You must have justification. This is a big, bolded, underlined, now highlighted word for a reason. Justification is super important. You have to have a reason for every step that you solve, or every step you do in solving a problem. When writing mathematical proofs, we use postulates and theorems as our justification. So this justification is our evidence, the theorems and postulates. All right, so here's a few theorems and postulates that we already know. We have corresponding angles postulate, which says that corresponding angles are congruent. The alternate interior angles theorem that says alternate interior angles are congruent. The alternate exterior angles theorem that says alternate exterior angles are congruent, and the same side interior angles theorem that says same side interior angles are supplementary, which means they add up to 180 degrees. So those are things that we've already learned. We know those go with parallel lines cut through by a transversal. Now we have a few more, and some of these things you probably have heard before, or they're things that you might have assumed. But these are some theorems that we need to know in order to solve our proofs. So starting from the top, we have the addition property of equality that says if A equals B, then A plus C equals B plus C. In other words, 1 plus 3 is the same as 3 plus 1. And let's go ahead and write down that example. So we have 1 plus 3 equals 3 plus 1. Subtraction property of equality. If A equals B, then A minus C is equal to B minus C. So if we have A and B subtracting the same value and A and B are the same, then their value will be the same. The multiplication property of equality says that if A equals B, then A times C is equal to B times C. So if A and B are the same, if you multiply them by the same value of C, then your value is still the same. The division property of equality. If A equals B, then A divided by C and B divided by C, as long as C isn't 0, are equal. So, again, if A and B are the same value and you are dividing out the same quantity from each of those, then they should have the same value. The reflexive property of congruence, or the reflexive property of equality, and I will reference it as the reflexive property of equality. All of these I'll reference that way. Says that everything is congruent to itself. AB is equal to AB. Okay, that one kind of sounds like common sense. 1 is equal to 1. 2 is equal to 2. Symmetric property of equality. If A equals B, then B equals A. All right. The transitive property of congruence, or of equality. If A is equal to B and B is equal to C, then A is equal to C. So if A and B have the same value and B and C have the same value, then A and C must have the same value as well. Then we have the substitution property of equality that says if A equals B, then A can be substituted for B in any expression. And the distributive property that says A times the quantity of B plus C is equal to A times B plus B times C. All of these things are things that you have done in algebra in basic solving skills. You just maybe didn't know that you were using this property or that that step happened because of a property. So now we're going to take a look at a proof's form. So we're going to go ahead and flip to the next page. So a proof takes two types of forms. You have tables and you have paragraphs. We're going to start with tables, but more specifically, we have geometric proofs. A geometric proof begins with if and then statements. If and then statements. These are hypothesis and conclusion of a conjecture. And we'll talk about what a conjecture is in a little bit. In this class, we will do proofs in a two-column format. And we're going to stay in a two-column format. Everything in a column can be written as a paragraph. And when you get into some more advanced math classes, your proofs will be in a paragraph form. So this is just an introduction, so we're using tables. After this, tables will go away and we'll use paragraphs. So we have our hypothesis, and the reason why is because it's given. We have some step that we solved because of some theorem or property. Another step because of another theorem, property, or definition. A third step, property of something, tells you you can do it. Conclusion, by the definition of something. So every line that we write happens because of some property. So this isn't telling you how to get to the next step. This is telling you how you got here. So you do a step and you say how you got there. You do a step and you say why you got there. So these things are specifically the reason why you can do something. Let's go ahead and look at an example. On this example, we have given EG equals FH. Prove that EF is equal to GH. So we have our statements here, and I am giving you 5 boxes here. There should then be 5 lines in your proof. Now, if you take a shortcut or if your proof goes a little longer, then you can adjust as needed. But for the most part, you're going to be using the number of boxes that I give you. So I have given EG is equal to FH. The given line is always the first thing that you want to write in your proof. That's always the first line. So I have EG is equal to FH. And I know that because it's given. So the reason why I can write this here is because it's given. That's our hypothesis. That's what we're trying to find. Then I have my prove line. EF is equal to GH. So as I'm working through here, I'm trying to end up with EF equals GH. We don't know why that's going to happen, but I do know that that's where I want to end. All right, now I want to take a look at what's going on in this problem. So I have EG is equal to FH, and as I'm looking at this, I'm noticing that from E to G passes over F, and F to H passes over G. I'm also noticing that F and G are in both segments. But I'm going to take a step back and go back to E to F, F to G. So E to G is equal to E to F plus F to G. So let's write that down. So in line 2, I have EG is equal to EF plus FG. As I'm looking at this, I'm noticing that I'm adding 2 segments together. So the property that I'm using is the segment addition property of equality. The segment addition property of equality allows me to take one segment and break it into 2 pieces that add together to be the whole. So this is really the addition property of equality, but I'm adding segments together, so I add the word segment in front of it. If this were angles, then I could write angle instead. But it's from the addition property of equality. All right, So I have EF plus FG equals EG. I already noticed that FH is made up of FG and GH. So I'm going to go ahead and make that my line 3. So I have FH equals FG plus GH. Same property, segment addition property. I took two pieces, added them together to be a whole. Segment addition property of equality. All right. Now, as I'm looking at these things, I'm recognizing that I said that EG is equal to FH. So that means that I can substitute what I know to value EG in place of the EG in our given line. So I have, instead of EG, I have EF plus FG is equal to FH. But instead of FH, I'm recognizing that FH is now equal to FG plus GH. All right. And I know that I did that and could do that because of the substitution property of equality. All right. So now I have these 4 lines, and I know that my proof line should be last. So there must be something that's happening from here to allow us to get to here, to say that EF is equal to GH. So let me look at what I have here. EF plus FG is equal to FG plus GH. Just notice something. FG is in both pieces. So if I subtract FG from both sides, that's going to leave me with EF equals GH. So that's what I'm going to do. So the reason why I can go to line 5 is because from 4 to 5, I subtracted. So that is the subtraction property of equality. This time, I am just subtracting numbers, so I don't have to put anything to describe it in front of it. So this is just the subtraction property. I'm having trouble spelling property. Property of equality. All right, so now we've done one example. We're going to go ahead and flip to the next page where we will have another. On example 2, it says, given that the measure of angle AOC is equal to the measure of angle BOD, prove that the measure of angle 1 is congruent or equal to the measure of angle 3. All right, so just like before, first thing I'm going to do, take my given statement and put it in the first line because it's given. So I have the measure of angle AOC is equal to the measure of angle BOD because it's given. And I also know that I want to prove that the measure of angle 1 is equal to the measure of angle 3. We don't know why, but I know that's where I want to end up. We'll figure out why later. All right. As I'm looking at this, I'm recognizing a couple things. One, I'm starting with angle names of letters and ending with angle names with numbers. So at some point, I'm going to need to switch over. And as I'm looking at these things, I'm also noticing that angle AOC is made up of 2 separate angles, angle 1 and angle 2. So I'm remembering that in our segment question, the last example, we had to add 2 pieces of a segment together to be a whole. So I'm going to try that same thing with angles. I have angle 1 plus angle 2 is equal to the measure of angle AOC. So AOC is equal to angle 1 plus angle 2. I can do that because of that same property, the addition property of equality. But this time, I'm adding angles together, so I'm going to include that descriptor in front of it and say that it's because of the angle addition property of equality. All right, so that's angle AOC. Let's see what we notice about angle BOD. Angle BOD is equal to angle 2 and angle 3 added together. So let's write that down. The measure of angle BOD is equal to angle 2 plus angle 3. Technically, we should be adding the m in front of these to say measure of. I'll add it in the next line. All right, so we have the same exact reason for why we can do that. We took two separate angles and added them together. So that is, again, the angle addition property of equality. Angle addition property of equality. All right. So now I have angle AOC, angle BOD, what makes up both of them. And I'm noticing that, again, I have this given statement, and I now have two different values for each of these things. So I'm going to go ahead, and in my next line, I'm going to substitute them. So for the measure of angle AOC, I have instead now angle 1 and angle 2. So I have angle 1 plus angle 2 is equal to the measure of angle BOD. But I also know that BOD is now represented by something else. So instead of angle BOD, I'm going to write angle 2 plus angle 3. Angle 2 plus angle 3. And I was able to do this line because of the substitution property of equality. All right. Now let's see what this line says as a whole. Angle 1 plus angle 2 is equal to angle 2 plus angle 3. Look at that. Angle 2 is in both sides. So if I subtract 2 out from both sides, that leaves me with the measure of angle 1 is equal to the measure of angle 3. So the reason why I can go from step 4 to step 5 is because of the subtraction property of equality. And that's what our last box is. The subtraction property of equality. All right. So now, some of you might be thinking, well, how do I know what theorems, postulates, and definitions are available for use? Well, they're written inside this packet and some of the other packets that we've already had. So all definitions, properties, and theorems that are inside of your notes packets, those are the things that qualify to be a reason here. Now, my in-person students, you all have dictionaries that we've been creating for the past several months. Those are your resources for what can go in the reason boxes. The properties of equality that we got in this lesson, we'll put those in shortly. All of those things from your note packets, those are your reasons. And we'll continue to get a few more of those as we go. All right, so now that we've talked about a couple proofs itself, we need to talk a little bit about some basic reasoning skills. So we're going to scroll up here, and we have something called inductive reasoning. Inductive reasoning is used in a lot of different kinds of proofs. We also have, beyond geometric proofs, there's something called inductive proofs, or proof by induction. Inductive reasoning means a process used to make conjectures by looking at patterns. And again, conjectures, we'll talk a little bit more about that really on the next page. So let's jump ahead a second and then we'll come back. So a conjecture is right here. We will come back to what we're doing with this, but a conjecture is an unproven statement that's based on observations. All right, so let's go back a page to inductive reasoning. A process used to make a statement, an unproven statement, by looking at patterns. So you're reasoning based on patterns you observe. So in example 1, we're going to determine the next two terms. A term would be one of these in each pattern. So I have a triangle, a square, a pentagon. So what I'm noticing is I started with 3 sides, then I had 4 sides, now I have 5 sides. So next would be a hexagon, so I'd have 6 sides, and bear with me as I draw one of those. We noticed by now that my drawing skills are not the greatest. Alright, so there's my hexagon, and I'm going to label that because it's not very clear. Hexagon, and then after that, after 6 sides comes 7 sides. So we have 1, 2, 3, 4, 5, 6, 7. And that is called a heptagon. And I know it's not very clear. My sides are kind of hard to see, I'll be honest. It's not a very good heptagon. But that's what it is. So label it. Do your best to draw one. If you're not sure exactly what this should look like, just Google one. You'll find one. Alright. So that is inductive reasoning. We noticed a pattern and we said, okay, this must be next. We're assuming that this is where this pattern is headed. And this is a pattern. And you might notice a different kind of pattern. If that's what you're noticing, then please let me know. But this is the one we're going to stick with. All right. On the next page, we're back with conjectures. A conjecture is an unproven statement that is based on observation. It's an educated guess. So it's kind of like you make conjectures in science class all the time with your hypotheses. So a conjecture, an educated guess. So for example 3, make a conjecture for each scenario. A, the square of a negative number. Okay, so let's try one. If I'm squaring a negative number, let's try negative 2 squared. Negative 2 squared is equal to positive 4. Okay, let's try another one. Negative 3 squared. Negative 3 squared is equal to positive 9. So my conjecture is that the square of a negative number is always positive. And we know that to be true, but we don't know that because we haven't proven it. So that would be a conjecture. The product of 2 odd numbers. Okay, let's multiply a couple odd numbers. 3 times 5 is equal to 15. Okay. Let's do 7 times 3. 7 times 3 is 21. Okay, let's try 7 times 5. 7 times 5 is 35. What I'm noticing here is if I multiply 2 odd numbers together, my product is also an odd number. So the product of 2 odd numbers is always odd. There's another conjecture. It's a statement, an educated guess that I'm making that I have not proven because I've observed something. All right, and next we have a counterexample. A counterexample is a specific case for when the conjecture is false. And you only need to prove one false item in order to prove the entire statement false. So we're going to find one counterexample to show each conjecture is false. So we have triangle ABC is a right triangle. So the measure of angle A is equal to 90 degrees. Okay, so we said that angle ABC is a right triangle. And we gave one example for measure of angle A. Well, what if the measure of angle A was 30 degrees? And the measure of angle B was 90 degrees. And the measure of angle C was 60 degrees. Well, then you have triangle ABC that is a right triangle, but A isn't 90 degrees. So that means that this has to be false. So I can say if the measure of angle A, or I could even say if the measure of angle B is 90 degrees. So if measure of angle A equals 30 degrees, the measure of angle B equals 90 degrees, and the measure of angle C is equal to 60 degrees, the conjecture is false. So we would then say, then the measure of angle A does not equal 90 degrees, and the conjecture is false. And I am aware that's a run-on sentence. You can probably write that in a nicer sentence than me. Okay, letter B. If two angles are complementary, then they are congruent. Okay, well, complementary means that we have two angles that add up to 90 degrees. So I have 30 degrees plus 60 degrees is equal to 90 degrees. But is 30 degrees equal to 60 degrees? Because it says if they're complementary, then they're congruent. Is 30 degrees equal to 60 degrees? No, they're not. They're not equal. So since 30 degrees is not equal to 60 degrees, then the conjecture is false. So we would say the conjecture is false. All right, this is where we are going to stop for today. We're going to pick back up with conditional and biconditional statements in our next video lesson, and then we will continue with proving some theorems we know in our third section.